So I'm going to talk about post-quantum signature aggregation. And I think the talk will probably not take all 30 minutes, and so we'll have time for questions and stuff, discussion at the end. Okay, so the sort of layout intro, I'm going to talk about elliptic curve, cross-input signature aggregation. I'm going to talk about post-quantum, or I guess better, post-elliptic curve signatures and aggregation there. Talk about a new potential opcode and wallet usage, then questions. Okay, so intro is, hi, TABConf is awesome. Thanks for being here so early. Please ask questions. Okay, so people have probably heard about Eli Kerr-Crow in SIGAG. I think people call it SIGAG or EC, I don't know. Cross-input signature aggregation. It's something that it's an idea that has existed, I don't know, 2018, 17. People were talking about it a little bit after SegWit of like, oh, once we do SegWit, then we should also do signature aggregation. And we can do Schnorr signatures. And I think when people were talking about like changing to Taproot, this was one of the ideas of like maybe the Taproot soft fork would also have signature aggregation built into it or something like that. The basic idea is if you have a Bitcoin transaction, this is a little off. Okay, you've got typical transaction will have a couple inputs, a couple outputs, right? Alice is paying Bob, and Alice has, let's say, a bunch of UTXOs in her wallet, and she needs to add up to these 3 UTXOs to send some money to Bob, and then she has a change output, right? So let's say she has input 3, 7, and 8. All 3 of those UTXOs sign, right? They create a digital signature, and you put the signature in that input. It's kind of inefficient if you think about it, right? Because they're all the same person. It's all the same wallet. You're signing 3 times. You're attaching these 3 signatures. Every node out there verifies this 3 independent signatures. Kind of silly. Why don't we just sign once, right? So instead of having 3 signatures, you just have 2 signatures. And this one signature, right, signature 3, it covers everything, right? So it's not like this signature only covers input 3 and you can malleate or change input 7 and 8. When you do sig hash all, like you sign the entire thing, right? You basically hash all the inputs, all the outputs, you sign the whole thing. So if signature 3 is signing, input 7 and input 8 are stuck there, right? If you try to change input 7 or input 8, the signature is no longer valid. So it seems like, yeah, maybe you can just sign once, right? The problem there, it's actually not risky for Alice. The problem is Alice can just point to Carol's input and say, yeah, that's my input. Those are my Bitcoins. I'm signing with input 3 for inputs 3, 7, and 4, but 4 is not even Alice's, right? It's a totally different key. It's someone else's money. It's not just that this, you have no proof that all 3 inputs are from the same wallet, right? So you do need all 3 of these inputs to sort of sign off on being in the transaction and sign off individually on the outputs. So the way elliptic curve cross input signature aggregation, or Eli Kerr-Crow input SIGAG, with 2 inputs, you have 2, A and B. Both inputs need to point to the outputs. How do you do that with one signature, though, right? Input B needs to sort of sign off on signature A without signing. So the way it works, and this is a huge simplification, is you add the signatures. And with elliptic curve properties, like you can do this. It's basically sig A plus sig B. And that plus symbol is doing a lot of work. There's like many papers and many equations and but you can do this, right? You can sort of combine these signatures in a way where they both need to be signing the same things. And if they're not, the addition doesn't work. So what are the benefits here? A lot of the benefit is space, right? And verification time as well, to some extent. It's not like, oh, I have 10 inputs, I aggregate into one signature. Okay, now the verifier only needs to verify one thing. There's some scaling that does add additional work to the verifier per input. But you do save a lot of space, right? And this is interactive aggregation, right? There's another idea of non-interactive aggregation, which is like a miner or someone in the mempool. Like, let's say you see 2 transactions in your mempool, and you say, well, I'm going to aggregate these 2 signatures, right? There's like Alice signed her transaction, Bob signed his transaction. I'm going to smush these signatures together and then relay it to my peer and say, well, here's 2 transactions, and I smush the signature together for you. That, as far as we know, is not really possible with SecP 256K1. It is possible with some other fancy stuff like BLS curves, and that would be really cool because then you could aggregate the whole block. But this is what I'm talking about is just interactive signature aggregation. It saves space. I think the problem, and I think this is purely my opinion, is one of the reasons it hasn't had as much work behind it and as much like, oh, we really need to get this into Bitcoin, is it doesn't save that much space, right? The elliptic curve signature is around 64 bytes, slightly higher with pre-Taproot, but around. And so you already have this 75% witness discount, right? So if it's in a witness field, it counts as 75% less. So this 64 real bytes turns into 16 V bytes. For the average transaction, it's around 8% savings in terms of V bytes. And there's nice statistics from this Blockstream research. There were people working on cross-input aggregation. That's like, I don't want to dismiss it, right? Because if you're long-term and Bitcoin's worth already trillions of dollars and people are using this, like an 8% savings on fees could be billions of dollars over the course of years. So I think it's like super important and really cool research. But at the same time, it's like, well, 8% isn't huge, right? Like it doesn't seem to be like the first thing we have to work on here for scalability and space savings. So that, in my opinion, that's maybe why it hasn't had as much drive to get into Bitcoin. So now there's a little quantum leap. There's been talks about quantum signatures a bit. Okay, so there's post-quantum signatures, and I don't even really like the term quantum. So like my personal opinion is like I'm not very worried about quantum computers. I actually think both these things are unlikely, but I think it's probably more likely that there will be some kind of regular old computer algorithmic deficiency in like the elliptic curves we're using than a quantum computer comes and runs Shor's algorithms. Both I think aren't going to happen. I'm not worried about either. But it's like, yeah, who knows? Like someday someone would be like, yeah, Pollard's row, we got a better way to do Pollard's row and find private keys from public keys on these elliptic curves. And there's a paper and people are like, oh shoot. And maybe it starts as like a small speed up, but it's like, hey, this is getting sketchy. We should move to different totally possible that we have to move to different signature algorithms, regardless of whether there's a quantum computer or not. I don't think it'll happen, but just in case, it's good to be prepared. And so there's different signature algorithms that do not rely on elliptic curves. And elliptic curves, are broken by Shor's algorithm if you have a quantum computer. The main downside is they're a lot larger, right? They're like 50 times larger. Like 4 kilobytes-ish is the size for the Sphinx Plus. You can get it lower, so there's I think that's another interesting part of research is like, hey, it doesn't really need to be 4K. Could we, maybe 3K? Maybe we can whittle it down to 2K. But like that's what we're starting with, and I don't see any way you get it down to anywhere close to 64 bytes. Okay, but so how bad would that be if we had to switch? Well, that's like a 50, you're down to 2% of the throughput rate that you had. So if people thought 1 megabyte blocks were small, now you've got like 50K or something or less. Yeah, so 20K. You're really restricted in how many transactions you can do, and that's really bad. So signature aggregation would be amazing if you can do it with post-quantum or hash-based signatures. Because even with the witness discount, these things are going to be 1 kilo VByte, and you'd have, instead of 8% savings, even a transaction with just 2 inputs would have something like 50% savings. 3 inputs, you're getting a 60 something. So, very large savings in terms of how many VBytes you're saving here. And these post-quantum signatures, if you did switch, maybe you'd also need to crank up the witness discount. That's a whole other argument I don't want to get into. But a way to aggregate these would be really powerful. Okay, so let's do it. Let's aggregate Sphinx Plus signatures. So let's look at how they aggregate the elliptic curve signatures. And this, like none of this, okay, so yeah, it's a kind of, but even if you know what all these things, and I don't endorse exponential notation. I like the multiplicative. Anyway, but can you multiply hashes, right? That's what this big pi thing means. You multiply stuff. I guess you can multiply them? Modulo what? Modulo 2 to the 256? What's the generator point for SHA-256? Is there one? I don't, none of this fits, right? None of the techniques that people have been working on for years of all these cool things like Frost and Roast and Musig2 and signature aggregation, half aggregation, none of this applies at all to hash-based signatures. Lattice signatures as well, although some people are like, hey, maybe there's a way to do aggregation with lattices. I'm pretty skeptical because I do want to say that with elliptic curve signature aggregation, I remember this in like 2018. Everyone thought it was going to be easy. It was like, yeah, you just add the signatures. You add the pub keys. You add the points. You add the R points. You add the S. It all works. And then it was like many years. Like there's a reason it's called Music 2. Like Music 1 didn't work. Well, anyway, it was a lot harder than we thought. And so I think with like a lattice thing where like, oh, there's hints that it may be possible. If it's easy, just add, translates into like 5+ years of hard work, then it may be possible. It's like, yeah, that's going to be decades. Anyway, so none of these things fit with hash-based signatures or lattice. Is there another way? So, and this is what I came up, I don't know, there's maybe better ways. This is just a way I came up with like, I don't know, a month or two ago thinking about this. We don't actually need to add the signatures or combine signatures, right? What we need is, you want the inputs to point to the outputs. And so if you think about like opctv, if you're opctv is op check template verify, where you basically like take the whole shape of a transaction and put that in an output. That counts, right? That's quantum secure because it's just hash based, and you're sort of committing to a whole other set of outputs in a quantum secure way. It's just hash based. It is sort of like a signature in that sense. It works, but it's very inflexible, right? You need to know what you're going to do in order to put that into your output. So it's not really usable for normal transactions because you don't know when you generate an address, you don't know where you're going to send money received at that address, right? You're like, okay, here's a new address, give me a Bitcoin. Okay, now I need to spend it. Well, if I have to decide where I'm going to spend it, even if I can enumerate, it's like, well, I know I'm going to send it to these 3 different places. And then I could put it into 3 different little opctv outputs in the taproot tree. So you could do that, but that's very restrictive, right? You generally are like, I want to have the Bitcoin, I want to be able to send it anywhere after the fact. Okay, so the basic idea is that inputs point to other inputs. The idea is if one input signs, all the other inputs can sort of point to that input and say, that guy's signature. So now we just need to know about inputs instead of outputs at address creation time, which is doable, right? So when you're creating an address, you may know other inputs that are going to be spent at the same time in the same transaction, right? So here's the basic idea. This is a fully signed Bitcoin transaction, 3 signatures, 3 inputs. You take 2 of the signatures away, and then you put these little pointers, right? You say, well, instead of a signature here in this input, I'm going to put a pointer to the first input, or input 0, right? Input 3. And same here. These other 2 inputs I'm spending in this transaction point to the input that has an actual full signature. So how do these pointers work? How does input 2 point to input 0 without signing? What we do is input 0's out point. So these words are hard. The out point is the term for like the UTXO label. It's just TXID index. So when you create a transaction, it's got a TXID, and then let's say this transaction has 2 outputs, and so you'd say like this TXID 0 is this UTXO, this TXID 1 is this UTXO. So that's called an out point. And yeah, so the idea is you bake the out point of input 0 into input 2's taproot tree. And so that means that input 0's UTXO needs to exist before input 2's address is generated. And the way you enforce this is a simplified version. I'll go to the actual version, one more slide. But basically, you just have an opcode that takes in an out point and says, okay, is this out point also being spent in this transaction? If so, great, success. If not, fail, transaction, is invalid. That's basically it. It's a real simple opcode, right? You do need to do a couple things. You don't need to, but the actual thing I'm going to propose, and I wanted to write up this for the mailing list before this talk, but it didn't quite happen. But I will post these slides and make a mailing list post probably, maybe on the airplane back. You want to put 2 extra things, this input index and this nonce. So the idea is the input index is where in the current transaction that's being validated to look for this output index TXID. And then nonce is discarded, but it's just a random number you can put there, and it gets discarded, has no consensus meaning for blinding. I'll talk about these 2. The input index is where to look in the transaction. So for example, if we're here, this, Alice input 7, so input 1 in the transaction, would say 0, whatever this out point is, and then some random number, because it's like look in position 0 for Alice input 3. If you don't have this, technically it's O event squared, right? Because if you have 1,000 inputs and they're all saying, hey, look for these other, inputs, then it's technically like each time you add an input, it adds how hard it is to search. So technically n squared, so you put this, it's like 2 bytes, whatever. You put that in there. And then the nonce, this is, there is a potential privacy leak here, right? If your addresses are sort of pointing to the other UTXOs that you own, if you use a new key each time, just from looking at the address, you can't tell. That's blinding enough. But once you spend it, people are like, okay, I know that key. Let me try to grind through and see what other things he was committing to in this tab tree. And so if potentially, that could be used for chain analysis, try to de-anonymize addresses. In this case, you're already de-anonymized. You're sort of already saying, yes, these inputs are linked, right? These are the same software or entity or coordinating entity. But you might have other things that you didn't link that are committed to, and so you want to blind those. So you put this, 16 random bytes or whatever. It shouldn't probably be random. It should probably be something like the hash of your private key and that out point that you're committing to, because then it's easier to regenerate after the fact. But yeah. So when you're using it, you'd put these elements in the actual taproot tree, right? So you'd have your main key. Let's say it's a post-quantum, signature, post-quantum pub key at the top of. Well, I guess if you're using BIP 360, there's not really a top, but somewhere high in the tree. Here's your normal signature thing, and then you have some branches down here that have commitments to other UTXOs that you already have, and then the input index you leave empty, and so you push that onto the stack when you're spending. So you decide, once you build your transaction, you start signing it by putting these little indices. So this seems to work. It would save a lot of space. It's pretty simple. Implementation's pretty straightforward. It's probably like 20, 30 lines. The part that's a little complicated is wallets. So the idea is when you're a wallet, you have a bunch of UTXOs, or you start out with none. So the first time you're making a new address in a new wallet, you can't use any of this, right? Here's a new address. I'm going to use a full signature, full pub key. But once you've made a second address, and you already have a UTXO, you can point to that. You can say, okay, this wallet takes that UTXO information, puts it in the tab tree. Wallets should take all asterisks currently owned UTXOs and put them in the tree along with a post-quantum pub key. You want to make this deterministic. You want to have like a order to do this. It does kind of complicate wallet recovery, right? So if you've just got a seed phrase and you're using this, you can generate all your addresses, but a lot of your addresses will commit to UTXOs. And so now you're like, as soon as let me generate the first 100 addresses, and then, on address 0, I see a UTXO. Well, maybe address 1 committed to that. Maybe it didn't. Now I have 2 different potential addresses there. Technically O of 2 to the n, which is very bad. So you would definitely, for larger wallets, if you have hundreds of UTXOs, you can't do all of them, right? You should limit it to 10 or something. Then you've got like 1,000x slowdown for wallet recovery, which is probably fine. But yeah, I don't know. Do exchanges and people with thousands of UTXOs really care about wallet recovery from a seed phrase? Maybe, I don't know. But yeah, so it's doable, but you would need a bit of thought into how you design the wallets for this. So the thing is this would work fine today, right? You could make this opcode and put it into Taproot. It's probably pointless because signatures are so small right now. They're 64 bytes. And the minimum space to use this would be a bit more. It would be more like 70-ish, right? So like it doesn't get you anything. I guess it's a little faster to verify because the nodes, the verification nodes just like look for another input and don't have to do an EC operation. It doesn't save any space. But it is much smaller than any known post-quantum signatures, right? And there's some that are in the hundreds of bytes, but they probably, the ones that I think people are talking about and looking at as the most likely thing that we would have to use in Bitcoin would be like hash-based, because we're already depending on hash, like the security of hashes for Bitcoin. So yeah, going from 3 or 4 kilobytes to this is great. One of the things you sort of worry about is like, well, what about replays, right? You're not signing. Are these, once you reveal this kind of commitment, could it be replayed? And it's not using keys or addresses, right? So one of the things, an alternative you could think of is like, well, what if your address commits to another address, right? Your pub, in this pub key, you say, well, if this other pub key is signing, that's okay. That counts as my signature. That would also potentially work, but that would open yourself up to like replay attacks. So this doesn't have any replay problems because you're pointing to individual UTXOs. There's no way to make like cycles. Like you couldn't have a transaction with like 5 inputs and they're all using opciv because that would imply a hash cycle, right? That would mean like I've got your hash and me, I've got your hash and me, I've got your hash and me. It's like, wait, that's not supposed to happen with hash functions. It doesn't work well with address reuse, right? If you just keep reusing the same address forever, well, you can't use this, which is kind of a plus, I think. It is a little tricky in that if you generate many addresses at once, right? If you're like, I want to generate 100 addresses right now, and then I want to give those all to different people, then this doesn't really help, right? Because your UTXOs are all going to be independent. So it works better if you're like making an address, receiving, sending, making address, that kind of thing. And you can't really use xpubs and give it to people. I'm not sure you can do that anyway with post-quantum pub keys. So I'm not sure that's a deal breaker either. But the idea of like giving someone a smaller thing and they can just derive a lot of pub keys from that, maybe there's ways. But it's a little tricky. Okay, so those are some of the downsides. No cycles because they're all unique. But that's pretty much it. It would work with any signature algorithm. It could do it with elliptic curve, but kind of pointless. But Sphinx, Once, Lattice, whatever. So I think that's probably like I'm not like advocating like, oh, we need to soft fork this in or any quantum stuff. But it's just sort of like looking at all these quantum signatures and you're like, oh, there are a lot of problems here. And it's like, well, if you're going, if you do end up in a situation where you need to use this, I think an opcode like this, or maybe someone has a better idea, but something like this would help a lot, right? Because then it becomes very signature heavy. The witnesses are like 90% of the whole block, and it's like, oh, getting down the size with this would be great. Thanks for listening. I guess we have a couple minutes for questions if people have any. But if you tell me why it won't work, or if you have a better way, then great. Thanks. Cool.
Amazing work, good stuff, looks pretty cool. This only really works if you, this is on the transaction level, and it would only really work if you, for the one wallet, right? Like for integrating, aggregating signatures for multiple UTXOs in the same wallet, correct?
Yeah.
So this doesn't really like scale Bitcoin in a way that like say BLS block-wide signature aggregation would.
No. I mean, there's no reason to use it now. It doesn't. It only helps. It sort of like makes transition to post-quantum less horrible. But
this could maybe like be good for maybe exchanges.
Yeah, they could save a lot of space, because presumably they have a lot of UTXOs and they're doing a lot of consolidation transactions a lot. So that they would be the primary, like they would save a lot.
Okay. The other thing I just want to make sure maybe you can draw your attention to someday is isogeny-based PQC, because it's basically like elliptic curve is in higher dimensions. You can do things like SIDH and other things, and it might be possible to. It might be a bit more powerful than this, but pretty good work so far.
Cool. Thanks.
Thank you.
Oh, and on that, like coin join is another thing where it's like you can commit to an input if it's multi-sig, as long as you have one of the keys in there, or so there's ways to do it, but it's not like, oh, this is awesome, we should use it now anyway. It's more of a, well, if you're stuck going to hash-based signatures, this helps. But today, you don't need it.
How does the rest of the blockchain understand that Alice input 3 and the signature there is good for Alice input 7?
So signature 3 still covers, you're using sig hash all, that doesn't change. So it still covers input 7 and 8. Right, so this signature does sign off on this whole thing happening.
I understand that, but the input 7, you're saying input 7 is using a redirection that is not a signature.
Yeah.
So how does the rest of the blockchain understand that let's say I pull in an input that isn't mine, what fails?
Okay, so if Alice input 7 doesn't have, basically Alice input 7, that address, has Alice input 3's UTXO label baked into it. And
Baked
so
into it.
Yeah, it's in the taproot tree, right? So the idea is like down on the left somewhere, there is a this, like op CIV with the TXID and index of Alice input 3. And so even if that exists, people aren't going to know where it is. You know, you're only the wallet can sort of prove that and show it to the world. And if it's someone else's address, that pointer, you know, that hash-based pointer doesn't exist at all, and so you can't show it.
And so that's one branch of the tree, but that's not. Okay, so I understand. So Alice input 7 is created so that revealing that part of the tree, which is what Alice input 3 in quotes means.
Yeah, it's got the hash of Alice input 3 in it.
Got it.
Yeah, I should have made a little tree where it's like, here's your regular pub key, and then down here you put your opciv clauses. But
yeah, thanks for this great nerd snipe. And like one thing I was thinking about while you were still talking, for the really, really large wallets, do we run into maximum depth limits of tab trees? And also, maybe for efficiency reasons, we want to limit the number of UTXOs we commit to. And then it becomes a very, very interesting problem in which order you have to spend your UTXOs, otherwise you make some of them unspendable.
I mean, you would never make it, so like, yes, that's why I sort of put this asterisk where it's like, oh man, that seems kind of, what is the optimal way to do this? I don't know. But you do want to, I think, like, yeah, restrict it to like pointing to 10, because you don't need to point to that many. You only need to reveal one. So you don't need to like commit to hundreds, because, you know, you just, as long as it does complicate also transaction construction, where you're like, oh, I want to minimize my transaction size to minimize fees. And like, now what you do, it's already hard, right? It's a subset sum problem. So it's already like, oh, I need to pick all these things to get to the right amount. But now you add this constraint of like, some of them point to others, and so they get free signatures, and some of them don't. So yeah, it's kind of a mess. But I think I would not, you could, but I would not encourage anyone to say, I'm going to only put CIV spends. I'm going to, you know, always have my like main signing pub key at the top, and then these are like options. So I never get stuck where like, oh shoot, I spent all these other inputs. I can't spend this one because the only way I spend this one is alongside these others. But I mean, you could, but like, don't. But yeah, but it does. But the like wallet design and transaction design, that's the complex part. It's not. I don't worry too much, because it's like, it's complex to optimize, right? If you do it in like a pretty, you know, oh, we'll just brute force, we'll just do it like the simple way. It'll work. And worst case, you don't get the space savings you could with the optimal way. But yeah, it is like, how should you do this? And that would be a fun thing to work on. Cool. Any other? Good. Well, next is Floresta stuff, right? Cool. Thanks, everyone. Thanks.